Subscribe to this YouTube channel by clicking the subscription button below. For future webinars and online short courses, please visit our website at australianwaterschool.com.au. Well, welcome to the Australian Water School webinar brought to you by IceWarm. And we're so glad you could join us today to discuss smart technologies that will improve our water services. It's going to be presented by Peter Seltzikas and Luke Dix from South Australian Water, commonly called SA Water. My name's Trevor Filler. I'm the National Partnerships Manager here at IceWarm and the webinar chair. And like I said, great to have you here. Once again, the webinar has attracted a global spread of attendees from many countries. You can see on the map on your screens. There we go. Yep, thank you, everybody. It's going to be an interesting time, I think. Well, there's a few upcoming webinars, free webinars and courses across a diverse range of water management issues. You can see there, I won't go into each one. We might look at it later, but you can see we cover a fair field and we're doing a webinar almost every week. I'll look at it. Yeah, well, yes. No wonder we're busy, huh? But right now, we're going to introduce Peter and Luke. Peter's a senior manager. He's on the left with the glasses. Asset manager at SA Water. Peter leads the operational capital investment planning for South Australia's largest water utility, managing 14 billion. You must not sleep at night, Peter. $14 billion of infrastructure assets, more than 20 years experience in the oil, gas and water industry. And secondly, Luke at SA Water is a data scientist at SA Water. Luke's instrumental in the continued evolution of SA Water's smart network, significant role in the development of the utility's initial wave of smart technology in Adelaide's central business district. And it's a great greeting to you both, Peter and Luke. Thank you so much for joining us.
Thank you.
What I'd like to know is what gets you up in the morning to do this? Say, Peter, what's the driver behind this?
Yeah, thank you, Trevor. Thanks for the question. It's pretty simple for me. Our emphasis and focus as an organisation is to continually strive to deliver better outcomes for our customers. And so
it's a bit quiet. Just bring the mic up.
Sorry.
I've got that. Better outcomes for customers.
Our emphasis and focus is really about continually delivering great service to our customers.
Yeah.
And so for me, it's very much about what a great and as you'll learn, what a great opportunity to integrate innovation and a passion for continue looking for better ways of doing things with what we're here for, which is all about delivering better customer outcomes.
It's an economic improvement too, though, wouldn't you say, for SA Water? I'm digging around here.
Yeah, definitely. There's value generated from using smart technologies in different ways, and value that comes from being able to plan work rather than having unplanned work, right. And also about taking the opportunity to focus on using technology such that it helps even defer capital investment over time. So very much an economic opportunity.
This keeps you awake a fair bit, I'd imagine, Luke. So what would be the same thing that motivates you most?
Yeah, I just think that it's a pretty exciting field to work in. There's lots of opportunities to really improve the way we deliver services, and I think really like the focus of this is for us is about understanding how we're going to deliver services into the future. And so some of the things we do don't have the outcomes that we were sort of searching for. Some of them, the exciting ones, are the ones where we start to see the outcomes we're really we're aiming for, and can see how we can embed that into the way we deliver services. So
there's a bit of unknown in that, a bit of risk, but when we're heading toward better outcomes in the future, you're going to get some wins and some not so much, some losses. You're not going to win on everything, but I hear where you're coming from. I've just looked through your slides, and the word future stands out to me quite hugely. Well, look, why don't we get this thing cranking? Peter, you're going to go first, and then going to hand over to Luke. And like I said, everybody listening in, great to have you. And let's put in, oh geez, some names there I know well. Greetings, Graham, Andy. Yes. Well, anyway, lots of other people there I should mention. Not mention just one person at a time. Thank you very much for joining us, everybody. Love to have your questions, and the more interesting questions and comments, the better. Makes a great discussion. So do chip in your comments. Over to you, Peter.
Thank you, Trevor. And look, also thank you to the Australian Water School for giving us the opportunity to talk about what we, as SA Water, are finding a very exciting initiative, and has been something that we've been working on over the last couple of years, and that is very much a part of our future moving forward. Today we are going to talk about the evolution of smart technologies in improving water services, and we're going to spend the next hour just talking about really the why, the what, and the how. So why have we decided to invest in smart technologies? How have we gone about doing that, and what are the benefits that we've achieved? What are the benefits that we've achieved as an organisation? And I'm going to give an overview of what we've gone about doing, and then Luke's going to deep dive into some of the really interesting areas that we've been able to evolve from the perspective of better use of data analytics, real strong use of data science, and how those things are helping us better understand our infrastructure and ultimately delivering better services to our customers. So I'm going to, just by way of context though, SA Water is an organisation that is South Australia's largest water utility. Our vision is to deliver world-class water services for a better life. Our focus is very much about delivering services to over 1.7 million people in South Australia across the entire state. And to do that, we employ over 1,400 capable and committed people that are working across the state on a daily basis, focusing on delivering high quality, reliable services in terms of water and wastewater services across the state. And we employ over $14 billion of assets, and we own them, we operate and maintain them, and we have a large contracting workforce as well as our own people operating these assets on a daily basis. But one of the challenges that we obviously face with our infrastructure is that, and it will become clear in a minute, in terms of the opportunity that smart technologies brings, is a lot of our assets are buried, and we have over 27,000 kilometres of water main, and it's all buried and it's very difficult to understand how it's operating. So that's one of the big challenges that SA Water has with such a large diverse asset base, with a lot of it not being seen. But coming back to SA Water's vision, we are all about delivering services to customers, and really the genesis for us in the context of smart technologies was really starting to ask questions about what do our customers really want from us, and what do they want us to continually focus on, and how do we deliver better services to our customers moving forward into the future. And to give some context, and to give some more detail around that, over the last few years, we've been working really hard on having strong dialogue and continuing dialogue with our customers. And over time, we've been able to develop some insight into what our customers desire from SA Water. The first one, and it absolutely makes sense that the first thing that our customers really strongly desire is safe water. They want to be able to turn on the tap and know it's safe to drink. But coming second is this issue of minimal interruptions. What our customers have been saying to us is that they want to make sure that we're doing everything we possibly can to minimise the interruption, not only to their water supply or their wastewater service, but also as they commute to work and as they're moving around in the community. They want to minimise. They want us to be minimising the disruption to their lives by failures in our water network. So they want their service to be more reliable, continually being focused on providing reliable service. And something that, and the third aspect there is about ensuring that our prices are low and stable, and we provide a stable service stability. So when we continue to think about, well, how do we deliver better services to our customers, instead of focusing on the more traditional mechanisms of potentially more capital investment in renewing pipes, we started to think about, well, how do we get a deeper insight into and deeper understanding of our infrastructure and how it's behaving, and how do we move from potentially reacting all the time to things that are going on to predicting, and that's where the idea of utilising smart technology was born. To make sure that we're all on the same page about what smart technology, when we talk about smart technology and smart networks, to make sure we're all on the same page, I just offer this graphic. So to SA Water, the scope of a smart network has evolved, and ultimately what it really has become is the concept of deploying sensors in some sort of pattern across our water and in the future, and increasingly our wastewater network, collecting information from those sensors collecting information from those smart sensors through different forms of data connectivity, and really introducing things like IoT, storing that data, then being able to analyze it and using predictive analytics to actually drive a better interpretation of the information, and then taking some form of action. And so that's the structure and the scope of a smart network, and I'll continue to talk about the smart network, but if you keep this sort of this model in mind, that's what we mean when we talk about smart network. So our evolution of smart technology, the use of smart technology, has been a gradual path since December 2016, when we decided to roll out a pilot in this Adelaide Central Business District. And we got that going in July 2017, and because we had such a significant amount of success very early on with that project, we then progressed to a statewide rollout of different types of smart technologies in February 2018, and we're continuing and we've continued to progress with that, and now we're considering an even broader rollout of different sorts of smart technologies to help us deliver better services for our customers. So I'm just going to talk about some of the examples of what we've developed and delivered to date, and how that's helping us better understand our infrastructure and be able to better respond to things that are changing on a daily basis. So the first rollout of a smart network occurred in the Adelaide Central Business District. We rolled out many different types of sensors across the Central Business District in order to really help us start to better understand what sensors can do, and how they may be able to help us really with that goal of minimising service interruption. What we ended up doing is creating, in effect, a demand management zone in the Central Business District by applying 11 mass flow meters. We also put in 11 mass pressure sensors. We installed over 100 smart meters to help get a better understanding of where the water was flowing and at what times dynamically. We implemented 23 pressure transient monitors so that we could better understand pressure transients, and Luke will talk a lot more about that in a moment. because we had some view that pressure transients in the network were quite significant, and if we could manage pressure transients, we might be able to defer or better manage and get more life out of the assets in the central business district. And finally, we implemented 305 acoustic sensors. The acoustic sensors have been deployed to really, in effect, listen to the noises that the water network is making, and try and identify, because of changing sound waves and sound information, try and identify where there might be a leak in the network that we might be able to go and fix proactively, rather than allowing it to come to the surface and have customers deal with the disruption that a leak may cause. So, just touching on acoustic leak detection systems. So we've deployed that. It's a daily, we get noise files every day. They're 9 seconds long. Our system analyzes, we bring that information back, and we analyze through developed algorithms that data, that information. Our key objective is to detect noises from the developing pipe leaks and intervene before the significant failure. And the success of the function is very much being driven by having sensors strategically placed in the network. How we've developed the analytical methods. We've also been able to better understand the timeframes over which pipe breaks do occur, and how to connect what noises in effect mean, so that we can better understand and differentiate between a leak and something that might just be background noise. And so ultimately, the success that we've had with deploying this sort of technology is really represented in this picture. The picture on the left-hand side is where we've identified a leak before the pipe has broken. We've utilised the technology to triangulate and to identify exactly where that leak would be on a pipe. We've dug down a small hole, identified the pipe, found the leak and repaired it. The picture on the right is what happens, unfortunately, when we have pipe failures that are uncontrolled and they happen almost instantaneously, and then we've got the job to go in there and do a reactive repair. You can see the level of the level of disruption that starts to cause to customers' flow, and also to the community, and the disruption that it causes to traffic and those sorts of things. So there's a really good example of the sorts of things that we're now able to do by utilising acoustic technology to help us better understand where there might be leaks. The second one that I just wanted to touch on was transient pressure monitoring. The emphasis here is really about recording dynamic pressure fluctuations that happen almost instantaneously, and it's very much, and what we've been able to do is be able to map, firstly identify where pressure transients are in our network, and then really be able to start fault finding to identify where they're coming from. And I'll leave it to Luke to talk more about some examples around how this has helped us actually start to change the pattern in the network, and the opportunities that come from potentially network calming the network as a result of identifying pressure transients and where they're coming from, and how you can actually manipulate them and change and calm the network down as a result of pressure transients. The third aspect to the Central Business District Smart Network was installation of customer meters. We installed 100. What customer smart meters were installed for was to help us better understand the dynamics of the network. But what they've also, but they've had an added benefit, and the diagram represents what we've seen in multiple cases where customers, upon installing a smart meter, we've been able to help customers identify that they actually have a leak on their side of the property, and this is the graph that's been provided is a real scenario where we identified that the customers pipework developed a leak, and we were able to talk to customers about the fact that they were losing water and significant quantities, which would have cost them money, and we were able to help them work out where that leak was and resolve that problem. So the customer was able to not endure ongoing losses over long periods of time. Because of the success of the Central Business District Smart Network, we as an organisation took stock of the success and started to think about where we could apply smart technologies more broadly across the state, and then secondly started to look at how we could integrate new technology, new smart technology that could help us, could further help us in reducing interruption to customers, help us reduce our and help us continue to increase the life of the existing asset base. So we progressed with trials of dynamic pressure management in one area of Adelaide, in Stonyfa. We've continued to roll out smart metering with an opportunity to invest in smart metering to help proactively manage leakage on the network. We've also progressed and broadened the use of acoustics to other significant areas of Adelaide where there's opportunity to use acoustic technology to continue to minimise disruption in North Adelaide, and looked for opportunities to broaden demand management zones, so where we're having challenges with leakage, and we've applied that sort of technology to an area called Port Lincoln, which is in a regional area outside Adelaide. We've also progressed with wastewater trials. So we've looked at utilising technology to deal with the challenges that present issues for customers around trying to prevent overflows from our wastewater network, and also looking to see whether we can use smart technology to better monitor the odour coming from our network, and see whether we can proactively manage odour as the events unfold that cause odour, and to contribute to influencing the odour patterns throughout Adelaide, and therefore the impacts to our customers. So to give you an example of now how we're applying smart technology to wastewater, we've installed multiple sensors in one suburb in Adelaide, being the suburb of Stonyfa, where we've implemented a network of sensors to give us a better understanding of things like flow levels in the mains themselves, better getting an appreciation of flow in connections to the sewer network, but also getting an understanding of temperature within the flow within the network, because temperature can actually give us some indication of whether there's infiltration coming into the network itself, causing increased flows in the wastewater network. And what we've been able to find since the system went live in November 2018 is we've been able to proactively identify a number of scenarios that probably would have led to an overflow, some within the mains themselves, and some even in the network connections where overflows can occur in a customer property if the connection is blocked. And so what you're seeing on the screen right now is the flow patterns across one connection, across one sensor point, that showed that we were potentially having issues on, say, the 1st of August, where we had quite a significant increase in the height of the flow in the sewer main, and we went in with a CCTV camera and identified a blockage in the pipe itself, which we were able to clear and avert an overflow, and most importantly, avoid disruption to our customers. So that's the sorry, and the last thing that we are doing is looking at extending our use of smart technology across to applying it to our trunk water main network. The central business district was very much about reticulation pipe, but we're now moving to our trunk water mains and using different types of technology. So rather than an acoustic sensor, moving towards hydrophones, with a view to recognise, and our emphasis and focus on our trunk network is about really about reducing impact to road users. Many of our trunk mains are going down main roads in Adelaide, and we're wanting to reduce the impact to traffic, which occurs when we have large water main breaks, and so if we can utilise technology to help us identify and proactively repair failures that might be developing, then it will be a good thing, and it will help us minimise interruption to the broader community. So I'm going to stop there, and I'm going to hand it over to Luke, who's going to do some deep diving into some of the technologies and some of the analytics that we've undertaken to give you a better appreciation of what we've learned and the success that we're having.
That's great. Thank you very much. Luke and Peter, maybe come on both on screen for a tick. There's just a couple of things here. We didn't look at the poll, which everyone, so we thank you for doing that. We wanted to look at this poll before we began, but let's get to it now. Have a look at this result here. Thank you everyone for answering those poll questions. It gives us a bit of gives us an idea of where you're coming from. So what sector? So look at that, mostly commercial consulting. A good balance out with the water authorities. We probably expected that, didn't we? That's good, thank you. And do you work in the water sector? Yes, by far majority there. Were you aware of the SA Water Smart Network? Half and half. Some yes, some no. Are you currently interested in adopting similar technology? And quite a range, as we would have expected, wanting a high interest in adopting this technology. Any thoughts? That's what you sort of expected?
Mm-hmm. Yeah.
That gives us an idea though, everyone. Thank you for participating in that poll. That's very useful. Really appreciate it. That's great. And just one question before you get going, Luke.
Sure.
Philip Grimm from Aquify in Germany has said, what is the non-revenue water quota of SA Water?
Non-revenue water is currently somewhere between 10 and 15%.
Yep, that's great. No, thanks, Philip. That's a good question. All right then. Well, let's get cracking with the second part of it then on your presentation, Luke. And everyone, keep asking questions and keep making comments, discussion points. That's really good. Hit the Q&A button. We'd have a good discussion if you can do that. Over to you, Luke.
Wonderful. Thanks, Trevor. Yeah, so just going to take a bit more of a deep dive into two of the systems or capabilities that we've developed. So the acoustic leak detection system primarily is, I would say, by far our most mature system that we've worked in. And I just want to talk a little bit more about pressure transient monitoring. I think that's probably of a fair bit of interest to a number of people. So so we'll start with acoustic monitoring. Sorry, I'm just trying to change the slides here. There we go.
Yep, that's clear. That's good.
Yep. Yeah, this is probably, as I said, one of the more mature systems in terms of definition of end-to-end process, from collection of the data through to the analytics, raising of field requests, and then through to the eventual repair that can happen. Just at the outset, what I want to say, and this is probably something that we've got a lot more appreciation of now after operating the system for 2 years, but I think it's often overlooked with technology projects, the value of humans within the system. So often when we're delivering these projects, we look to deliver something that's end-to-end system or system improvement that that the technology can provide. And I think that we've come to the realization that humans are really critical in the performance of this system. So and you'll sort of see that in this slide, which is a bit of an overview of the overall process. In terms of the evolution of this capability, it's been a really collaborative process between SA Water as the utility and the asset owners, the University of Adelaide, to provide some, I guess, technical expertise and research expertise. And also Allwater, who are our operating partner in the CBD. So we've had a really close team of academics, technical people, asset owners, and the operators on the ground that have really contributed to developing this capability. So if we look at the process from end to end, you'll see, I guess at a high level, the system comprises of two things. So we've got the permanent acoustic monitoring capability. So there's the 305 loggers, the acoustic sensors that Peter introduced before, and there's also a mobile field capability, which is really critical. So we start with the permanent acoustic monitoring, 305 across 125 kilometres of pipe in the CBD here. So we don't cover the whole lot. We cover around 60 to 70% of that pipe work. They send the data back. We've got a team of analysts from the University of Adelaide and SA Water, actually monitoring and analysing the data, and turning that into basically a number of requests. So there's alerts that are raised, they're analysed, and then there's a refined number of requests to the field to actually go investigate whether there's a leak there.
Yep. Sorry to interrupt. If this is okay, Philip made an interesting question on this particular slide. Philip mentions you mentioned predictive analytics. How many of these 1,000 to 1,400 acoustic alerts are real leakages?
We will come back to that. So
yeah,
so that's a bit of a preempted question. Yep, we'll come back to that shortly.
The other question you had was, you mentioned predictive analytics. Are you also predicting water demand, floods, price, etc.?
We, in other tools, not in this project, I would say we have that's taken care of in another part of the business, the water supply group. They have energy price modelling, they have demand forecasting, that sort of thing. We haven't had historically a huge focus on leakage. So Peter mentioned before, we're around 10 to 15%. I think last year it was 11%. That's quite low non-revenue water by global standards. And yeah, historically we haven't had a huge focus on leakage. So really the focus of this leak detection system from us, our perspective is around trying to avoid the incremental impacts associated, or the consequences associated with with undetected
Yep.
pipe failures.
Yeah, no,
Thanks.
that's good. You've flicked up a couple of questions here that keep rolling in. How many people are required to analyse this data?
Yeah, so we've got at this stage, again, I'll come back to that later, but at this stage, and probably for the 2 years that it's been operational, well, there was a lot of work in trying to understand the system and and develop that expertise to begin with. Now we're looking at probably one person, when they get the refined list or the refined number of alerts, one person for about an hour a day, roughly, does the desktop assessment. Then there's two people. So we're only covering 100, only focusing on the CBD here. There's two people that are the field expertise. And they're doing all sorts of things from sensor maintenance through to the response and identification of the cracks themselves.
Yep. We might be going a bit too far here, but from New Zealand, Tim Barry from Water Care Services asks, what's the size and number of field mobile units required to service the area you cover?
Yeah, so we've got 305. There's 305 sensors. They're all accelerometers, so with magnetic fixture. So they just basically pretty small footprint within our existing chambers. So they attach to either valves or fire plugs. So it's all existing infrastructure. What can I say? It's probably the future the future model of what these sensors might look like might change, and we've got some ideas about that through some of the challenges that we've faced. So yeah, in terms of the pace that this was rolled out for SA Water, the accelerometers were the right choice. They're quite an easy installation. It's just a magnetic attachment to the existing assets. So.
Yeah, well, we'll leave the questions there for a moment, and there's a couple more coming in at the moment. We'll head straight back into your presentation again. Just thought it might be useful while you're touching on some of these things.
No problem. Yeah, we'll come back to a few of them anyway. So, okay, so just in the middle box there, I've got identification of pipe crack or other fault by field team. That is where that expertise lives in terms of the field expertise. So there's two guys there. That bit there's really, really crucial. So we're not sending out repair crews to dig up roads or actually respond a full crew to something that's not a fault, or it might be a private customer leak, or it might be a leaking valve, and we send the wrong crew. So that's a real fundamental piece to this system, and a really good set of expertise that we've developed. From there, if it's identified as that crew will be able to locate it, basically pinpoint it to where it is, and they'll have a very good idea of what type of leak it is. So whether it's on a connection, whether it's on a meter or a network fitting, or indeed on a pipe, which is really the ones we're chasing. From there, we basically it enters our normal repair. So we have a lot of crews repairing water mains all over the network, so right across the metro. So it enters the same sort of scheduling processes there. But the added benefit that we've got with this permanent monitoring is that we can actually continue to monitor the progression of it and make sure that it's not progressing and doesn't need an increase in urgency. Yeah, that's probably the overall process. So we've got there approximately 1,000 alerts per week for the acoustic detection system. A number of processes are done to reduce that to just a handful, basically, of field requests. So when there's a field request, we haven't got a lot of it's a very low rate of false positives. So yeah, I'll come back to them in a sec. I'll just want to give a couple of examples of the types of things that we see here. So This example's from pretty near to the start of actually when we rolled it out, and there's some pretty basic analytics happening to identify this. So if you look on the bottom left plot there, what that bar chart actually represents is 6 locations, 6 different sensors around this event. And the height of them actually represents the baseline noise. So that's actually the minimum night noise. So yeah, it's the baseline level that the noise gets up to in the middle of the night. So if we trend that in the absence of a leak, what we're expecting is that to go quite low. That can be affected by all kinds of things happening in the environment, but generally we're expecting that to remain relatively low. What you see there on the 23rd of July is one of the loggers increasing quite significantly from one day to the next. So that's the point that often potentially we wouldn't react straight away unless we had crews available, but we probably wouldn't react straight away. We would leave it for the following day to make sure it wasn't some sort of environmental influence on that reading. That could be things like construction works or someone actually consuming water, that sort of thing. The following day, we saw that again and actually increase. So at that point we raised it for alert, and you can see the outcome there. So water starting to surface pretty lightly there, and when we dig it up, you can see the amount of water coming out there. You'll notice that that's or if you're familiar with managing water mains and managing water networks, that it's a circumferential crack there. So it's one that's typically attributed to external ground movement or external loading on the pipe, and that's quite a clean back-breaking crack. What we see from them a lot from the couple of years we've been doing this is often they crack and they don't really progress too much. So they jump up baseline and then that baseline remains relatively constant, and often don't typically lead to the larger sort of main breaks or I guess community disruption that Peter showed before. The real interesting ones is where it's a small crack, it's developing, and there's really early signs. There's some really early indicators that it's there, and we're not quite sure. That the resultant break from this is often quite rapid, but there's an indication prior to it that to the major break happening that it was there. So what we've got here, I've shown 3 basically noise plots at 3 times. These are about 2 weeks apart. So you can see evolves relatively slowly, and definitely sufficient time to respond to that. So you can see sort of in the frequency time plots that are on the bottom left, that there's a whole bunch of horizontal bands there that are becoming more and more lively as the crack progresses. If you look on the top right there, that's a power spectrum density plot of the 3 events, and what you can see is specific frequencies coming a lot more lively. Some of them remaining the same as the baseline, but then certain frequencies becoming a lot more lively as the crack develops, and when we dig it up, that's the crack that you can see in the bottom right. So it's one that's slowly propagating as there's pressure cycles on the pipe, as you know, as the cyclic loading continues to occur, that crack just slowly opens up more and more. In terms of, so this is probably answers a few of these questions. So we'll just get back to the operational response here. So roughly 1,000 acoustic alerts today, a week. Some of them are in development. Some of them are far less we consider sort of relevant or lower priority. So really we boil that down to around 30 to 40 priority alerts each day, and they're the things that the hour and a half of desktop analysis really look at. From there, they turn that list of 30 to 40 priority alerts into around 12 to 15 requests for field investigation and confirmation a week. So that's around 50 to 60 a month. So that's how busy our field expertise actually is. And just by way of a case study, the plot there shows what them 12 to 15 investigations actually result in being. So there's all sorts of things from valve leaks, construction works. There's a few false positives in there, and then at the end there's the main breaks, which the month of March represented 4. In terms of improving this system, we just going through a process now of a lot more advanced acoustic analytics. So we're really looking at automating that manual analysis of the data to identify the suspected faults and request the field attendance. So we want to remove that expertise of analysing the data out of it. We're not looking to remove the need for a field attendance and verification. So there's a few ways we're doing that. Our algorithms processing the sound magnitude, similar to the night noise, but slightly more advanced than that. And that's really sort of a pattern recognition type approach. Algorithms processing the frequency spectrum. Again, that's similar to a pattern recognition approach and looking for small emerging frequency bands of interest. And then we're also applying machine learning or AI processes on trained a trained process to identify sounds which sound like leaks. So we've got So they should be able to distinguish leak sounds from other normal sounds in the network. That's the acoustics. I'll move on to pressure transient monitoring. Peter sort of mentioned before, really the aim of this for us is around calming the network. It's a focus on reducing the overall load placed on our pipes, and really what we're looking for there is avoiding unnecessary pipe breaks. In the long term, we're looking at avoiding fatiguing loads. That's an interesting field, particularly pertinent to plastic pipes, but also the interaction between corrosion and crack propagation from cyclic loading. In the short term, though, really we're looking at avoiding stresses which I'll put in inverted commas break the camel's back, but pressure loading that actually leads to failures. This is an area that probably I'd say we're less mature in than the acoustic monitoring. In terms of the process definition, we've got a lot of expertise in understanding pressure transits as a phenomenon and how they propagate throughout the network. But in terms of really continually delivering services, we've maybe got a little way to go. And what I'll say is that this is can be a bit of a silent beast. So I think it's relatively something that can be easy to ignore. But I think from some of the stuff that we've seen, that's probably to the detriment of longer term asset health and certainly the performance of a network. And I think that we've probably got a little way to go with understanding the link between exposure to transient activity and also the condition or asset deterioration. But I don't think that that's really necessary to build a case from what we've seen to build a case for doing something about it. So for us, we're quite interested in identifying the source of the transients and doing something about that, as opposed to transient individual event detection. In terms of where the transients come from and the source of them. There's a few sort of areas, and probably familiar with these. So manual operations in terms of our own network operators, but also third parties accessing our infrastructure. So fire services, that sort of thing. Actually introducing pressure transients, changing network conditions, so areas where we've got air entrapment in pipes, changing the pressure behaviour, control equipment, so pump stations, control valves, actually producing pressure transients, and also customer connections, which I've got an example in just a moment. Yeah, I think that probably in the longer term, the real application for us is around identifying the sources and managing them proactively rather than sort of I guess using these to inform prioritization processes, that sort of thing for water mains. This is really around managing the day-to-day operations of our network. And as an example of that, this example comes out of the Adelaide CBD. This was first detected on one pressure transient logger, and basically it was a consistent event that was happening, had a consistent time of day, consistent magnitude. We knew it was a consistent sort of event. After sort of triangulating, moving loggers around, we're able to pinpoint the source of it. So it happened to come from a building, engage with the building, and what we found is that they were actually testing their fire system weekly and introducing pretty large pressure transients into our network. So that's led to sort of engagement with the technical regulator for fire systems here, the MFS here, and engagement with these asset owners. Yeah, that's the sort of the approach that we're taking with this. I'm going to just hand back that one to Peter, I think, now.
Thanks, Luke. What we've done hopefully over the last 50 minutes or so is give you a really good appreciation of where what we've done with smart technology and why we've done it, being continually looking to deliver better service outcomes for our customers. But we're not resting on our laurels there. We're certainly see a great opportunity for the future of smart technology in SA Water, and we're actively looking at different ways to apply smart technology to help us deliver better outcomes. So some of the examples that just mentioned on the slide that you have in front of you are things like we've recently, as an organisation, looked to enable a zero cost energy future. We're making a significant investment into generation, on-site generation of energy through deployment of a vast quantity of solar arrays, and we recognise that in order to best optimise the way we are able to utilise the deployment of the solar arrays and battery storage and the other energy producing opportunities we have, like utilisation of biogas from wastewater treatment plants, to be able to optimise the utilisation of that, we're having to think about different ways of being able to analyse the different factors that influence decisions, like what the energy market's doing, and be able to rapidly change either on-site demand or better utilise the energy that we are producing, and that's going to need really a smart thinking and deployment of smart technology to help us better achieve those outcomes. We're also looking at things like further deployment of things like smart metering, given the success we've had in the central business district around helping customers better better monitor their demands and their use of water, and some of the success that we're finding from deployment of smart meters to help with reduction in non-revenue water where there might be areas of higher non-revenue water than the average. We're actively looking to deploy that sort of technology to help in that area. And just starting to think about how else we might be able to control our water network, and that's really represented by the idea of the business of tomorrow. So how do we further integrate technology and smart technology to help us potentially control the network when we do predict failures, rather than having a static approach to network control at this point in time. And by that I mean having to go and send people out to go and turn valves on and off. Maybe we can use smart technology to help us identify failures, predict failures, and have technology drive the network such that it controls the flow of water to minimise the overall disruption. There's some of the things that we're thinking about, given the success that we've had and the value that we're seeing from deploying this sort of technology. So thank you.
That's been brilliant. Thanks so much, Peter and Luke. It's been a huge field to cover in such a short space of time. Can we just take a couple of these questions in this last minute or two? We've got about 2 minutes before we hit the 1 hour mark. Philip, a director of Aquify in Freiburg, Germany, has said, how do you handle this much data? You're producing a lot of data with 305 sensors in high time resolution. Maybe brief answers at this point, because we've only got a couple of minutes and there's a lot more questions we could go into. Thanks.
Yeah, there's quite a complex sort of system architecture that drives that. The pressure transient management, we've got a couple of tools. One of them is an on-prem server and proprietary tool that actually manages that. We can't pull in huge amounts of that data, so we typically call about 15 minutes of that transient pressure data. The rest of it's not too bad. So we're talking about for the acoustic monitoring, we're talking about I don't know how many data points a day. They're around one every 10 minutes. So that sort of frequency of data we're polling from how many devices? Maybe 5, probably 600 devices. So it's probably not huge amounts of data, but definitely the pressure transient data is quite large. It's almost a separately managed system, that one.
Yep. No, Newen, thanks for that. Thanks for your question, Philip. Newen is from Access HQ in Adelaide, South Australia, a senior test analyst. Please advise, what is the distance between two sensors? I guess it matters what type of sensors, doesn't it?
Yeah, it does. If we're talking about acoustic sensors, typically we see a range of around 100 meters. It depends on a huge amount of factors. So pipe material, pipe size, how good your connection is actually with the asset, whether you've got intermediate repair sections of PVC, whether you've got branches that can attenuate some of that sound. So your actual coverage, on average, we estimate that at around 100 meters. That's why we haven't got 100% coverage of the CBD. That's the acoustics, yeah.
Yep. So follow-up question from you. Do you automatically alert relevant teams once you detect any leakage?
From the acoustic desktop monitoring, yes, we do. We'll raise it to the field response crew. From there, they'll raise a work order that will enter our standard works management systems. So as though a customer's called the repair in, it just enters that normal prioritization process. Yeah, but it's straight away.
Yep. From Cairo University, Egypt, Ahmed has asked, what are the main reasons behind the majority of pipe cracks you've found?
In terms of types of failures, in Adelaide CBD, it's around 50-50 circumferential cracks versus pressure, longitudinal cracks or blowouts. Actually, it's slightly less than that. There's around 40% ground movement, circumferential cracks, and around 60% blowouts. So that's specific to the CBD. We have a lot of ground movement in other parts of Adelaide. So yeah.
We'll make this the last question. Ahmed from Cairo University has asked, it seems that the threshold used for acoustic leak detection is quite low, hence resulting in such a large number when it comes to the false alerts. Is that true, or maybe there's other reasons?
Yeah, it's probably true. I guess them numbers of 1,000 alerts down to 40 priority alerts was really us starting at. In terms of our advanced analytics, that is all about better processing of the data to raise really the most important ones. That there is basically a replication of what we're manually doing. So in our own minds, getting the computers basically to do them analytics. But that requires, at the moment, we think that's going to take 7 algorithms basically constantly processing and coming up with some sort of combined output that suggests there is something that needs to be investigated.
I said this was going to be that last question, but Ross Chandler's asked an interesting one. Ross is from Biosol in Victoria. Do you compare H2S data with the rate of corrosion in sewers?
We do compare. We do look at H2S levels and corrosion on sewers. Yeah, absolutely.
Look, this has been an absolutely fantastic hour, just slightly over, but you've delivered an enormous amount of material, and we really appreciate it, both of you. Thanks everybody for participating and the discussion and the questions. There'll be a feedback survey come up in just a moment automatically on your screens. Please spend 1 minute to answer the 8 or 10 questions, and there'll be a recording link emailed to you. You can see the 4 webinars immediately coming up across the next 4 or 5 weeks or 4 weeks. Sediment transport modelling, responding to climate change, they'll be really interesting. State and fate of Hindu Kush Himalaya water resources, very much climate change. And the last one for Rob Keller about pumps about to fail. Well, that's not the last one, that's the next 4 actually, and there's a lot more coming behind them. So do go onto our website or YouTube. You can see the details there on the screen. But we're going to finish there, and just want to say how much we appreciated your time today, Luke and Peter and SA Water. It's really been an interesting time. We want to hear the further development of this, because I can see there's tons more coming up, you would say. Any
Absolutely.
Final comments?
Yeah, we'd love to continue to share our journey in this really exciting area. Yep,
let's do it. Well, it's bye for now to everybody, and thank you again, Peter and Luke, and thanks for everyone for joining us. We'll see you at the next webinar. Bye for now.
Thanks, Trevor.
Subscribe to this YouTube channel by clicking the subscription button. For future webinars and online short courses, please visit our website at australianwaterschool.com.au.